Okay, good morning, ladies and gentlemen. I'm Richard Smith, representing Logic Forest Solutions. This is my work colleague and business partner, Ben Williams. Logic is a pre-harvest service provider specialising in pre-harvest services. We're a Gisborne East Coast based company and we were established in 1999. Now our services include forest inventory, harvest planning, road survey and design. Today we will discuss and present to you harvest inventory, logging systems, harvest planning, road survey, environmental considerations, resource consent, and road and landing construction. The objectives of today's presentation are to provide an understanding of pre-harvest engineering requirements, outline a systematic approach to the stage, and provide an understanding of required resourcing and infrastructure, and also highlight the importance of robust planning. Okay, so let's get started. Forest inventory. This is considered 1 to 2 years prior to harvest. It's basically a field data collection process where random plots are located out in the field at a 2% sample of area, and they are measured for quality characteristics, DBH, diameter at breast height, and tree height. So this data then gives us the ability to make informed harvesting decisions, timing of that harvest, target areas within the stands based on market conditions, and give us an indication of required annual cuts and sustainable forest cuts over the entire life of that forest. Okay, logging systems, we can simply categorise these into 3 basic systems or operations: ground base, swing yarder, or towers. Ground-based systems or operations are generally allocated on really easy terrain, so less than 22 degree slopes. They're undertaken with an excavator, a skidder, as you can see here. This is a highly productive grapple skidder, typical of any ground-based operation, probably capable of extracting 3 to 4 trees at one time. These ground-based operations are generally the most cost-effective logging operations. They have a gang day cost of around $6,000 per day, and an associated logging rate would sit somewhere between $28 per tonne and $32 per tonne. But this is typical of the East Coast. In the Central North Island, you could probably expect that rate to halve, simply because they have really easy terrain and highly mechanised productive crews. Okay, the next operations are the swing yarders. These are ideal machines for really broken, short, sharp slopes, typical again of the East Coast. They're generally dephased from the processing point, so stems need to be dragged back with a skidder to the landings where they are processed into logs. As you can see here, this is a swing yarder operation, and he's sitting right out on the edge of a ridge. So the dephasing makes it a real safe operation, and also they have the ability to extract stems off really steep slopes or sharp slopes going into incised gullies and waterways. Okay, next to the towers, 70 foot, 90 foot, 110 foot These machines are allocated for long, steep slopes. They require full landing capacity, so 2,500 square metres. The tower sits on the landing and the logs are processed on that same landing. These machines are very specialised, heavy equipment, high capital cost. They require up to 8 to 12 guys to run them. They require exceptional skill levels and experience. We can extract stems out to 450 metres. This machine here is a 110-foot tower, and at a real pinch, we could possibly go out to 600 metres. These have a really high capital or gang day cost, $9,000 per day up to, and associated logging rates would be at the higher end, $34 per tonne to $38. Okay, harvest planning. The aim of a good harvest plan is to safely extract and transport logs to market whilst minimising environmental impacts and maintaining a cost-effective operation. As you can see here, this is a recent cutover, so a recent logged area. These points here are strategically planned with matching new road grades planned to them. There are multiple considerations to any harvest plan, safety being obviously the most important, environmental constraints, QE2 covenants, DOC native reserve areas, riparian zones, historic and wahi tapu. This is pretty self-explanatory. These areas need to be identified and avoided. Utilities such as power lines, gas lines, telephone lines. Terrain and geographical, so slope stability, or soil stability, sorry, and slope class within that forest. External issues like local body. We need to be able to transport multiple tonnes of logs out of the forest and have the required infrastructure to transport heavy equipment into the forest. There are three key steps in preparing a harvest plan. The first is a draft plan or a desktop plan. This requires really detailed topographical maps. The aim is to maximise ground-based areas. As already discussed, these are the most cost-effective, so if we can maximise those areas, we're going to reduce our logging cost. We need to identify these critical hauler locations. A bit hard to see this slide, but these are planned hauler locations and associated roads graded to them. And we also need to plan for deflection. So deflection is simply explained as the sag or belly in the ropes. As you can see here, this is the hauler sitting up on the top left-hand area, and down here is our back line, and you can see where we've got lift. This means that we've got sag in the ropes. This enables us to fully suspend these logs. And so basically, the higher the deflection, the higher the payloads, the higher the daily production, the lower our logging rates. So really important from a planner's perspective to get this lift at the back. So the final stage is field verification. This requires thorough ground evaluation. We mark out our landings and mark out our appropriate new roads graded to those landings, prepare detailed engineering notes, and enter the verified plan from our desktop plan into GIS mapping software. Okay, road survey and design. The aim of good design is to set out our planned road from our harvest plan, which balances cut and fill materials and is designed to reduce earthworks and associated cost. So not all roads are surveyed and designed. However, you can see this road here, which links multiple switchbacks, traverses across a really steep slope. It's a typical road that we would design, lay out in the field, and this is going to avoid really costly earthworks mistakes. The design is carried out by Roadline software. This is specifically Canadian-based software designed for forestry roading applications. It's a series of windows. The profile view indicates road grade. The plan view indicates road alignment. The data view indicates cut and fill information and a cross-section of that particular road. So any interaction in any one of these windows will interact with the other three. Okay, set out, this is the final stage. We set out our designed road in the field. We use a Trimble Geo7 handheld GPS unit. The centre line is marked in the field, and also a top batter peg is measured out and put in the field with cut and fill information on it for the roading contractor. And basically it's follow the dots roading plan for the contractor. Okay, thank you. My bit's over. I'm now going to hand you over to Ben to continue.
Excuse me. Hear me? Okay, thanks Richard. I'm going to continue the presentation, briefly looking at the resource consent process and some environmental considerations, and then looking into road and landing construction. So a resource consent is required for forest harvesting in most regions and sets out rules to protect such things as pristine native bush, as we can see bounding this forest, waterways, archaeological sites, and downstream effects, amongst many others. The harvest plan and associated documentation are a key part of the application process. Once any issues are worked through between the forest manager and the council, a resource consent will be given, and it will have various conditions attached to it. The forest manager has various tools that he can use to mitigate adverse environmental effects. I'm sure many of you have heard of issues around forest harvesting and the slash generated. During heavy rain events, slash can be transported down waterways, and it can damage neighbouring properties and sometimes end up on city beaches. So here we have a slash catcher recently constructed out of railway irons and wire rope across the stream bed. And this is a picture of the same slash catcher following a heavy rain event, so you can see how effective it has been. We have other tools that can control sedimentation and erosion. Here we have a flume used to direct runoff across fill slopes and onto a hard surface. Here we have a berm, which you can see constructed around the edge of this road, again used to divert the water away from that fill slope and onto a hard surface. We have cutouts which are installed in haul tracks prior to a heavy rain event or at the completion of harvest, and these again divert the water off that haul track and prevent erosion and scouring. And then in more environmentally sensitive areas, we can have silt fences, which again trap that silt and sediment and slow water flow, so preventing scouring and erosion. So once the resource consent has been issued and operations begin, the first step in the process is roadline harvest. And this involves harvesting the trees off the corridor where the road is to be constructed. The road corridor needs to be of a sufficient width to allow sunlight onto the road to assist with drying. This will result in a firmer road pavement and reduce maintenance costs further down the track. Temporary landings or skid sites are constructed at 300 to 500 metre intervals along that road corridor, and the stems or trees are pulled to these landings and processed into logs. So once the road corridor has been cleared of trees, road construction can begin. And it's important that road construction keeps up with Roadline Harvest to ensure a steady uplift of logs from the landings and prevent bottlenecks between the operations. Here we have a typical forest road being constructed. Forest roads need to be of a standard capable of handling a 44-tonne logging truck in all weather conditions. So they are very costly to construct and maintain, and therefore their distance must be minimised while keeping within road grade, environmental and health and safety constraints. Typically we have three classes of road within a forest. We have our arterial roads, which are the main roads within the forest, which run off the highways. We then have our secondary roads, slightly smaller, running off the arterial roads, and then we have the spur roads, which run from the secondary roads out to the landings. These spur roads experience heavy and intensive traffic volume over a small period of time while that setting is harvested, and they will be constructed to the minimum standard that can safely handle logging traffic over that time period. Here we have a cross-section of a typical forest road. Not sure how well you can see this, but construction width, so the width from the base of our cut batter to the edge of our fill batter is generally 6 to 9 metres. This depends on the class of road being constructed and environmental constraints. Usually our first constructed layer is our sub-base, and that generally constructed out of a weathered rock source from within the forest, preferably as close to the section of road being constructed as possible. Our next layer is our base course. It's a medium-sized crushed metal from a quarry, usually applied at a thickness of around 200 mils across the road surface. And then in some sections of road we require a running course, which is a smaller sized crushed metal for sections like steeper road grade and where we need increased traction. This graph here summarises makeup of roading costs. On a typical East Coast forest road, the distance from the quarry to the forest was 25 kilometres. So as you can see, aggregates or metal makes up the highest proportion of that total cost, followed by earthworks. And just please note that metal costs can change significantly depending on the quality of the metal available and the distance from the quarry to the forest gate. Skids, an area where stems or the trees are pulled to and processed into the logs. Stems need to be, landings need to be of a sufficient size to allow for log stacks, a processing area, a truck turnaround area, a loading zone, and if a hauler landing, they need to be able to safely land 2/3 of the tree stem in front of the hauler without sliding back down the hill. Hauler pads, smaller landings that a swing yarder or a smaller tower can sit on. Stems are pulled to these hauler pads and then pulled with another machine to the landing, to the processing area. Waterway crossings, generally the larger the catchment and the larger the waterway, the larger and more expensive the piece of infrastructure needed to construct to cross that waterway. So some examples here. We have a large culvert. These need to be capable of handling the maximum flow in a storm event to prevent washout. box culverts constructed of concrete in the stream bed. Water can flow across these in a storm event. Ford's often the most cost-effective solution. This one here is constructed of concrete blocks embedded into the stream bed. And bridges obviously span the entire waterway and usually the most expensive to construct. This graph here shows a breakdown of costs from pre-harvest services right through road and landing construction to harvesting and transport of logs out of the forest. As you can see, harvesting and transport of those logs makes up approximately 80% of that total cost. And a quick conclusion, so in this presentation we've taken you through the pre-harvest processes necessary to bring your forest into a harvest-ready position. It is important that all these processes are completed in a timely fashion and interlinked for the forest owner to realise the maximum value from their forest. Thank you.